started. So welcome everyone to another session of NCTS Algebraic Geometry seminar. So today we are very happy to have Benoît Cadorel from Nancy. And he will talk about hyperbolicity of hypersurfaces and Green-Griffiths jet differentials. Please.
Well, thank you very much. Thank you for the kind invitation to present this talk to your seminar. So if I understand correctly, I am supposed to start by some introductory facts about the results I will present. So let me first begin by an introduction to complex hyperbolicity. So in this setting, the ideas are that we are trying to better understand the classification of projective manifolds and more precisely the manifolds of general type. So let me maybe begin by recalling what happens in dimension 1. So in dimension 1, so in the case of projective curves, well, of course, we have the uniformization theorem. And everything boils down to saying that if we know the genus of a curve, we have a lot of information. So for example, so let me maybe display the table in its entirety. So depending on the genus of the curve, so if it's 0, 1, or 2, we know that the universal cover of the curve will be P1, C, or the disk. And we also have a metric with a constant curvature, which will be either positive, 0, or negative, depending on the genus. So in higher dimensions, we don't have the uniformization theorem. So it's very wrong to have such a result would be trivially false. But we have other invariants that we can try to use to classify the complex projective manifolds. And so one of them is the Kodaira dimension. So maybe let me recall what it is. So assume first that you have a line bundle on your X, which is a complex projective manifold. And so the Kodaira dimension, oh, sorry, I forgot one very important invariant here. So the Kodaira dimension of your line bundle, or the Itaka dimension of the line bundle, is the invariant which belongs to either an integer between 0 and the dimension or minus infinity. I forgot minus infinity here. It's very important to include it. So it's the element such that it controls the growth of the spaces of the sections of the powers of L. So if you compute this H0 here, you look at the dimensions of the sections of L to some power, for n maybe divisible enough. And so if it's minus infinity, it will be always 0. And in the other cases, you have polynomial growth like this. And so what we call the Kodaira dimension, before that, we say that L is a big line bundle if this growth is maximal. So polynomial with degree the dimension of the variety. And what we call the Kodaira dimension of X is simply the Itaka dimension of its canonical bundle. So the canonical bundle being the determinant of the cotangent bundle of X. Okay, so if we look at the case of curves, then we can complete the table as follows. So we have minus infinity for genus 0, 0 for elliptic curves, and 1 for the hyperbolic curves, which constitute the majority of complex projective curves. And so in higher dimensions, in any dimensions actually, we say that X is of general type if this Kodaira dimension is maximum. So here, the curves of general type are precisely the hyperbolic ones, the ones of genus higher than 2. So you can see why we call them general type, because they constitute the majority of curves. And if we try to climb up in dimension, we have the case of surfaces, the next case. And here we have the Kodaira dimensions of the Kodaira classification of surfaces, which tells you that you can look actually at the minimal models of surfaces, the one with the Neff canonical bundle, at least with the Kodaira dimension inside Neff. And we are able to classify the surfaces in 4 cases, depending on their Kodaira dimension. But here you see that the ones which are general type are all the ones that we are not able to classify in any of the other classes on which we have much more precise information.
So minimal
So-
minimal surfaces.
Yeah, minimal surfaces, of course. So I said we assume that we have contracted all the -1 curves in this situation. So I say if you want that the surface is K3, if its minimal model is K3 in this situation. Okay, and so we would like to better understand the geometry of varieties of general type, and complex hyperbolicity is an attempt, if you want, to proceed to do this to attack this problem. And by so it's an attempt to better understand the geometry of varieties of general type by the way of studying their entire curves. So let me explain what it is. So an entire curve on a variety is simply, or on a manifold, is simply a non-constant holomorphic map starting from C and arriving in this manifold. So if we look at the curves, at the projective curves, we can try to understand if they admit or not entire curves. And we see that actually, so in the case of P1 or C, or P1 or elliptic curves, we have many entire curves on them, because we have many entire curves in P1, of course, and C is such an entire curve. The universal cover of an elliptic curve gives you such an entire curve. And in higher genus, the situation completely changes. So a proof of this fact that you have no entire curves on genus of curves with genus higher than 2 is simply the following. So assume that you have a map from C, a map starting from C and arriving in X, holomorphic. Then you can lift it to the disk, the universal cover of your manifold. And then you get a bounded holomorphic map from C then to the disk. And you have this Liouville's theorem, which tells you that actually F tilde has to be constant. So F was no entire curve in the beginning. And so in this situation, we say that X has a property of hyperbolicity. We qualify this property of admitting non-entire curve as being a complex hyperbolicity property. And so we say that manifold is Brody hyperbolic modulo a subset if any entire curve on X fall inside that subset. And we simply say that X is Brody hyperbolic, or just hyperbolic for short, at least when X is projective, if you can take this set to be empty, or in other words, there is no entire curve on X. So here you see that the curves which are Brody hyperbolic, the projective curves which are Brody hyperbolic, are the ones which have genus higher than 2. So we qualify them as hyperbolic. You see where this term possible justification for this terminology of hyperbolic. Okay, so as I said, we would like to better understand the geometry of varieties of general type. And one of the main conjectures in this field are that these varieties of general type should satisfy many hyperbolicity properties. And so one of the main conjectures is, well, the Green-Griffith line conjecture, which tells you that if you consider a complex projective manifold, then there should be an equivalence between the fact that first X is of general type, then, okay, maybe let me display everything first. Okay, good. So an equivalence between the fact that X is of general type, then with the fact that there is a proper algebraic subset such that this subset contains any entire curves drawn on X. So X is broadly hyperbolic modulo this subset. And also you have a property with a more algebraic flavor which should be equivalent to X being of general type. The fact that outside such an algebraic subset, all the varieties should be of general type, or more precisely, of all the subvarieties which don't fall inside this subset should be of general type. And as you see, I wrote subvariety and not submanifold. What we mean when we say that a singular variety is of general type is simply that if you take a desingularization of it, it is of general type. Okay. And even for the surfaces in dimension 2, complex dimension 2, this is very, very open. We have many different results if you make more stronger assumptions on the surfaces you are considering. For example, assumptions on their characteristic numbers. But in the general case, this conjecture is not known for surfaces. And maybe let me be more precise on that. Yes, as you recall, this table here shows you that the conjecture is, of course, true in dimension 1. So you have entire curves precisely when the curve is not of general type. The projective curve is not of general type. And so this is the fact that this conjecture is true in dimension 1 that motivates us at looking at it in higher dimensions. And maybe let me also say that there are more arithmetic, there are conjectures with more arithmetic flavor to them related to this one, which attempt to somehow generalize the Folting's theorem in dimension 1 to higher dimensions. So on a variety of general type, there should not be many rational points if the variety is defined over a number field, for example. Okay, but I will stick to entire curves in the rest of this talk and not talk about this third point, for example, or the points with are related to arithmeticity. Okay, and so more precisely, I will focus on a particular problem to in this talk, the case of hypersurfaces. So what happens if you specify this conjecture to the case of hypersurfaces? So you can try to determine when a degree D hypersurface in Pn+1 is of general type, and if you just have to compute their canonical bundle, and you have this adjunction formula which tells you that the canonical bundle of an hypersurface is just OD minus n+2 if I take x being of dimension n, so Pn+1. And so the hypersurface will be of general type if D is strictly larger than n+2. And so the conjecture, the Green-Griffith-Lang conjecture predicts that if D is higher than n+3, then X should be quasi-Brody hyperbolic, namely there should be a proper algebraic subset in X containing any entire. And actually, so here I didn't write his name, so Kobayashi predicted that if you allow yourself to assume that X is generic, and if you take degree, a larger degree actually, then X should actually be Brody hyperbolic and not just merely quasi-Brody hyperbolic. So this is a much stronger result. So this was predicted by Kobayashi. This is the Kobayashi conjecture. And what Kobayashi said is actually that if D is large enough, then this should hold, but the bounds here are predicted. We expect these bounds to hold because of some many different results of Clemens, Hein, Voisin, Pacienza predicted that for other reasons related to the study of subvarieties of X, then the bounds should be these ones, essentially because if you look at this conjecture, the third point here holds for very general varieties, very general hypersurfaces with once you have these bounds. So that's why we expect them to hold. Also, we expect a property of hyperbolicity with respect to curves to hold as well. Okay, and so we are very far from obtaining these results with, especially with these two bounds, but we have in the last decade obtained very strong results still. But assuming that the hypersurface is generic and also taking much larger degrees. So what was proved is that, I will present two different results in one. So that's why it may look in a logical viewpoint a little bit weird, but just bear with me for a moment. So this theorem predicts that there exist two sequences of, says that there exist two sequences of integers, dn and dn prime, such that if you take a degree D hypersurface, with a degree larger than one of these two sequences. Then for a generic hypersurface, then X is quasi-Brody hyperbolic. So this was proved in 2010 by Diverio, Mercure, Rousseau. And more recently, it was proved by Brodbeck that if you take a degree larger than dn prime, so of course, dn prime has to be larger than dn because the second result implies the first one, then X is Brody hyperbolic. So you have these two sequences of integers at the time. So in Brodbeck's results, the sequence was not explicit, dn prime. Diverio, Mercure, Rousseau gave for their sequence 2 to the power n to the power 5. So this is very large, much larger than this linear bound, as you can see. And the bounds were improved by many authors. So let me quote, well, Diverio, Mercure, Rousseau gave a bound for dn. Darondo, Demailly, Deng, Mercator also worked on this problem to improve the bounds, and at best they obtained such a bound. So an exponential of some constant times n log n, so n to the power of some constant times n. And quite recently, well, 5 years ago, Bergzi and Kirwan have obtained a polynomial bound in these results. So we are still very far from the linear bounds, which are predicted by this conjecture, but still this is much better than these super exponential bounds. And the way they proved their result was by using non-reductive GIT. So what I will present in the rest of this talk, in the second part of this talk, is that actually it was not quite necessary to use non-reductive GIT techniques to prove that you can have a polynomial bound, and you can actually use some very, well, I don't know if very old is the correct term, but some well-known tools that were known for at least, I think 40 years. And so these tools I will present to you right now. So the idea is to use jet differentials. So let me say that every one of these authors used jet differentials, but with a different flavor. And the last improvement by Bergzi-Kirwan was to apply non-reductive GIT techniques to these jet differentials. But here I will present jet differentials, what was known in jet differentials for at least 40 years. So consider a complex projective manifold and fix an integer k, which will be the order of the jet differentials we will be considering. And attached to this integer and your space x, you can define the jet space of order x, which is simply a space which will be fibered above x, that you can form by looking at all the kth order Taylor expansions, starting from the germ of the plane at 0, the germ of the complex line at 0, and arriving into x. So, of course, you can project such a Taylor expansion to x simply by sending this Taylor expansion to its value at 0, and you get a natural projection that way. And above any point, to define a Taylor expansion, you just need k times n a pole of complex number if you have local coordinates. And so the fibers are complex spaces of dimension n. Well, n is the dimension of x, and k is the order you are considering. Let me say that it is not a vector bundle, because if you change coordinates on x, well, the changes of coordinates you will have between your Taylor expansions will not be C-linear. So I will maybe give more details on that in the rest on this in the second part of the talk. But so the change of coordinates are actually given by the Fa-Di Bruno formula, and so they are not C-linear, and it is not then a vector bundle above x, but still a bundle in vector spaces. So a very simple example is what happens when you take k equal to 1, then the first order Taylor expansions like that are simply given by tangent vector to x. So one jet at any point. You can consider at any point the set of 1 jets, and it gives you the tangent bundle to this. So in that case, it is a bundle. But if K is larger than 2, then it is not a bundle anymore. So now you can state that you have a natural C star action on JKX given simply by reparameterization at the source of at the beginning of the map. So you can write it like that. So you have lambda that acts on this jet simply by multiplying the variable t by lambda. And what you can do now is you can quotient out this space by this C star, at least when you remove the 0 section given by all the jets which are 0. So you look at all the Taylor expansions which are trivial, which are constant, you remove them, and you remove this 0 section, and you quotient by C star. And so what happens is that on any fiber above X, you have this Cn minus K, you remove 0, and you quotient by C star. So it very looks like a projective space, but you have some weights actually. So maybe, yes, this weights. So the C star action is not simply multiplying by lambda any coordinates on this C to the power nk. Actually, what happens is that you have weights 1, 2, 3 until k that appear in this fiber, and each one appears n times. So you have nk here, which was the dimension of your fiber. So this is a singular space. So you have different ways of considering it. So maybe you may want to look at it as an orbifold or a stack, or simply a bundle in singular weighted projective spaces like. But in any case, on that space, you have, since it's formed using a projectivization technique, it admits a tautological line bundle, which I will denote like that. So it's O1 of that Green-Griffith jet bundle on XK. GG for Green-Griffith, of course. And what is the link with entire curves? So consider an entire curve on X. Then what you can always do is that you can lift it first to the JKX, the space of Kth-Taylor expansions on X, because simply you take a point in C and you look at the Kth-Taylor expansion of F at that point. So F is here, between C and X, and it gives you a lift to this space, to this affine space above this. And now, at least at the points where this map is not 0, where the Kth-Taylor expansion is not 0, you can quotient by C star and get a map from C minus some points to XKG. But this map now lands inside a projective space. And so you have this valuative criterion for properness, which tells you that you can extend the map across the points where Fk vanishes to a map starting from C and arriving in this projective manifold on which you still have this tautological line bundle. And now there is a very important theorem, which I will state that way, which tells you that C cannot land anywhere inside that space. Actually, it has to land in the 0 subset of some sections that you can form out of this tautological line bundle. So to do that, you have to pick some ample line bundle on X. And what the theorem tells you is that the image of this lift inside XK Green-Griffith lands, so sorry, I wrote the formula in one block here. So what you have here is what we usually call the augmented Bayes locus of this tautological line bundle. So what you have to do is you look at the powers of this tautological line bundle. You remove an ample line bundle coming from X, and you look at the sections of these powers here. And what the theorem tells you is that any time you take such a section, actually it vanishes on the image of Fk, of F tilde k, which means that F tilde k lands inside the Bayes locus of this line bundle. But this is true also for any M. And Okay, sorry. Here you have this under brace here, which should hold everything. Sorry. I wrote that the augmented base locus is just that thing. That is not true. This is the whole thing here with the inclusion, with the intersection as well. And it doesn't depend on A actually. So it's a subset inside this AK Green-Griffith, XK Green-Griffith that you can form using the tautological line bundle, and the theorem tells you that the image of the curve inside this AK XK Green-Griffith must land in it. And so it gives you a strategy to try to prove. So what we want to prove eventually is that on a given manifold, for example, a hypersurface, there is no anterior curve, or that they are contained inside some algebraic subset. So we want to restrict the loci where the anterior curves may fall. And so you have a strategy for that using the theorem I presented just above. So I recall what it tells you here. You have this lift, the image of the lift of the anterior curve must fall inside the augmented base locus of the tautological line bundle on XK Green-Griffith. And there now we will use that to prove that C must fall inside some well-defined locus in X. So again, K is fixed. It may vary in the future, but let's fix K. Inside this Green-Griffith jet space, you can always look at the set where the Kth-Taylor expansions have a 0 first derivative. So one thing that must hold for sure is that if you have an anterior curve, then the image here cannot land identically inside that space, or it will mean that F prime vanishes identically on C. So this image, if C is not constant, must at some point leave that space, but it must always fall inside that space. So what you can do is you can just look at the components of that space here, which are not contained inside this XK, well, the space of singular jets, which is defined here. And then Fk, F tilde K, must land inside sigma K. So Fk, if it be projected to X, must land inside the projection on X of this sigma K, and you call that the Green-Griffith locus of order K on X. And so a consequence of the fundamental vanishing theorem is that if you have an anterior curve C on X, then it must fall inside this Green-Griffith locus of order K for all K, actually. And it gives you a strategy to try to prove that actually you don't have any anterior curve on your manifold. You can attempt to prove that this locus is actually empty. And so this is precisely what has been done. So let me recall the theorem. So this is precisely what has been done in the theorems of Di Verrier-Rousseau and Vogt-Beck that I presented earlier. So the second version of their theorem, what is actually proved in their work, is that under the same assumptions, well, if D is large enough and X is generic, then you can prove that the Green-Griffith locus of order N, the same, well, the order must be the dimension of your manifold, X. Well, this Green-Griffith locus is not the whole manifold, and so the anterior curves must fall in it, and they must fall in the proper algebraic subset, which is this Green-Griffith locus landing in X, which is subset of X. And if you take degree even larger, then you can actually prove that this Green-Griffith locus, is empty. And then you get the Kobayashi conjecture. You prove that X was actually hyperbolic and not merely quasi-Brody hyperbolic. Okay, so this is the first half, the first half hour of my talk. So I'm planning to move now to the second part. If it's, I don't know if we are waiting for some time, or do I start immediately?
Maybe, yeah, are there any questions at this point? Could I maybe ask a question? So if possible,
Yes.
Could you please indicate a bit how the fundamental vanishing theorem is? Yeah, why do we expect that? Yeah,
So this is something that I was planning to recall. Well, not all the details, but I will explain in a few minutes that you can interpret this theorem also as the fact that any entire curve satisfy the jet differential equations that vanish on an unpole divisor. And so it is usually proved, this theorem, using Nevanlinna theory. But maybe if you want a quick heuristic idea behind it, is that assume, for example, that your entire curve is given by an elliptic curve. So assume that you have an elliptic curve inside your manifold X. And so what the theorem claims is that if you take differential equation, a holomorphic differential equation on X, which vanish along an unpole divisor, then it must vanish identically on your elliptic curve. And this is true because elliptic curves don't admit differential equations vanishing on an unpole divisor, simply because on elliptic curve, you have this uniformizing coordinates showing you that the bundles of differential equations are trivial. So maybe I can go back. The idea is simply that if you replace X by an elliptic curve here, or maybe an invariant, this completely trivializes. And so the construction is quite functorial. So if you do the construction on an elliptic curve, yes, okay. On an elliptic curve, sorry, this base locus will be the entirety of your Green-Griffith space above your elliptic curve. It will be the whole Green-Griffith space. And so if you assume now that you have a diagram constructed with an elliptic curve here, landing inside X, then you could put here the Green-Griffith space of your elliptic curve here. And you can see that since here, the intersection actually of this base locus here must be the whole thing once you intersect it with the Green-Griffith space above the elliptic curve, you have that this map must land actually inside this base locus. So the idea is simply that in the case where your entire curve is given by an elliptic curve, you don't have any non-vanishing, non-identically vanishing holomorphic differential equation that vanish on a non-pole divisor. And if you have an entire curve, then the idea is more complicated and you have to use Nevanlinna theory to control what happens if you restrict a differential equation to an entire curve. But I will talk a bit about differential equations in a few minutes, actually.
Okay, thank you.
Okay, so maybe I can start with so I had prepared a second. Okay. Okay, I can start whenever you want.
Yeah, we can see the slides. So
yeah, thank you.
Yeah, any moment.
Okay, well, thank you. So here now I'm going to present in a few more details the proof for hypervelocity of hypersurfaces, which was actually known for quite some time, and try to explain what was done actually by Berzzi and Kawan, so maybe very, very quickly, and to explain to you why actually we can just use the tools that I have presented to you and a few more that were known for, I would say, at least 15 years now, to prove that you can have this polynomial bound with a slightly higher bound than in Berzzi-Kawan result, but still a polynomial. So let me do a quick recap on the theorem of hypervelocity of hypersurfaces that I presented before. So, okay, so the result is as follows. So you have these two sequences of integers, such that if you take a degree D hypersurface, which is generic and of degree higher than the first bound, then you have hypersurface, which is quasi-Brody hyperbolic. So the entire curves must stand inside this inside the proper subset, which will turn out to be a Green-Griffith focus. And the result of Damian-Volpeck tells you that actually, if you take a higher degree, then X is Brody hyperbolic. So you don't have any non-constant holomorphic map. And Bergze and Kirwan, what they did was to prove that you could take polynomial bounds for these two values of D, as opposed to the exponential bounds that we knew before their work. Okay, so let me give you a few more informations on these jet differential equations, on these Green-Griffith bundles I was talking about earlier. So take a complex manifold and look at the spaces, fix an integer k, and look at the jet spaces j, k above x. So if you take holomorphic coordinates on x, local holomorphic coordinates and Euclidean chart, call them z1, zn, then you get the vertical coordinates on j, k, x, like that. So you just have to differentiate your coordinates on x and get coordinates which you can use for describing the Taylor expansions of jets arriving inside x. And also, you can look at the C-star action I presented earlier in these coordinates, and it will read as follows. So you have a lambda that acts on the order L coordinates, you derive at order L, simply by multiplying by lambda to the power L. So here you see that the first coordinates have weight 1, the second ones here have weights 2, etc., until weight k. So that's why that justifies what I presented earlier. If you quotient this space by the action of C star, you will see that you have C to the power nk quotiented by C star with weights 1, 2, etc. until k, and gives you weighted projective spaces. Okay, but you can do that. You can also try to describe this Green-Griffith jet space. So it's a projective bundle. You may want to look at it as the proj functor applied to some algebra. And this algebra you can describe as follows. So simply project the structural sheaf of jkx to x, and it gives you a sheaf whose sections are precisely the polynomials in these coordinates with coefficients, well, say the holomorphic coordinates on the base, well, holomorphic functions on the base. And looking at the weights of these polynomials, so these polynomials are in these coordinates dj to the power L, it gives you a weight, which I indicated by this m here. And so what happens here is that for each weight m, you get a vector bundle, which you can call, you will usually use this notation. So GG, of course, stands for Green-Griffith. And we use this notation omega to remember that these spaces stand on the side of forms on X rather than vectors, if you want. Vectors, the role of vectors is played by the points inside that space jkx. And on the dual side, coordinates on that space, we usually use this notation to denote them. And so, as I said, well, sorry, I forgot the Green-Griffith here. The sections of these vector bundles are polynomials in the ZJL with coefficients given by holomorphic coordinates of X and with weighted degree M. And now what happens is that, okay, if you take the spec of this algebra, you get back your JKX. So the relative spectrum of this algebra taken above X gives you an affine scheme lying above X if you want. And also, if you consider the Green-Griffith jet space, as I said earlier, this is given by jkx minus the zero section quotiented by C star. It is simply given by the projective functor applied to this algebra. And note that this algebra is locally generated by these coordinates, it's not generated in degree 1 only, it's generated actually in degree 1, 2, etc. until k. So this algebra, once you projectivize it, you get a singular variety. And as I said, the fibers are actually weighted projective spaces, which are in general singular, at least as long as, say, k is larger than 2 and also n is larger than 2. No, k is larger than 2. Okay, and so you have this tautological line bundle on xk Green-Griffith. Maybe I should put GG here. Okay. So I will use many different tautological bundles in the future, so I hope it will not get too confusing. I will try. Well, normally, I will not forget to put this GG anymore, I think. So you have this tautological line bundle on this projective algebra here. And as I said, this algebra is not generated in degree 1. So to be more precise, it would be better to consider it not as a line bundle. It is not quite true that it is a line bundle. Actually, it would rather be a Q-line bundle. You may look at it as a Q-line bundle if you want, or also as a norbifold line bundle. So as I said earlier, you may want to look at that space as a stack, Deligne-Mumford stack, rather than a variety, rather than a singular variety. And on that stack, this tautological line bundle is a genuine line bundle and not merely a Q line bundle. So I just simply say it's a norbifold line bundle. But this consideration will not be too important for the rest of this talk. And what you can do actually is, as always, you take powers of this orbifold tautological line bundle, and if you project it back to X, you get your spaces, your vector bundles of sections of weights M in your algebra. And a different way of looking at the vanishing theorem I presented earlier. So if you remember, I said that if you take an entire curve on X, then you can look at this lift here, and the image of this lift must fall inside the augmented base locus of this orbifold line. So what does it mean? It simply means that if you look at a section which is given by some power of this tautological line bundle minus an ample line bundle on the base, then Fk must fall inside the zero locus of this section. But the section of the power, the mth power of OK minus A, you can also interpret as a section of that vector bundle on X. And so take such a section, then you can look at it locally as a polynomial in these coordinates z prime until zk, so z1 prime, z2 prime, etc. until z1k, znk, with coefficients, holomorphic functions on the base on X. So this is a local way of writing sigma using the coordinates I presented on the previous slide. Okay, and so what this inclusion tells you is that this sigma, if you look at it as a section on this space, then it must vanish along the image of this f tilde k. And you can look at what it means on X. It simply means that you replace this z by the image of f, and you differentiate your entire curve in X, and plug in this expression, the different derivatives of this entire curve f. And so this must vanish identically on C. Well, it gives you a local way of writing this, this application of P to your f tilde. But if you look at it on the entire C, then it must be zero identically. And it is the meaning of this fundamental vanishing theorem, which you can say, which you can interpret, sorry, as saying that entire curves satisfy these global differential equations, which are defined by this section sigma, that vanish along an ample divisor. And what I said earlier is that assume that you have, so heuristically, if you want to see why this theorem should be true, is assume that you have an elliptic curve here, for example, which gives you your entire curve. Then pulling this back pulling this sigma back to your elliptic curve will give you the same thing on E. It will give you a section on your elliptic curve of this vector bundle minus an ample divisor on your elliptic curve. But on an elliptic curve, this is trivial. So this section, sigma, once you pull it back to your elliptic curve, gives you actually a section of a trivial vector bundle tensored by minus an ample line bundle. But there are no non-zero sections of this because you don't have any non-zero section of minus an ample line bundle on anything. So if you have an elliptic curve, this is also true for P1. So morally, the theorem holds for non-hyperbolic complex curves. This is quite easy to prove algebraically. And the content of the theorem is that in these ideas, you can replace non-hyperbolic projective curves by entire curves. But this is less trivial to prove. You have to use Nevanlinna theorem. Okay. So let me briefly recall what the Green-Griffith locus was. So this is a locus inside X, depending on the integer K you have fixed, which is given by projecting on K the union of the components of this augmented base locus, which are not included in the singular locus. Sorry, this should be XK Green-Griffith singular, the projective version. So let me recall that the singular locus inside this XK Green-Griffith is given by the kth Taylor expansions, such that f prime is 0. And so the content of the theorem, okay, so let me recall that briefly. What was proved by Diver and Merker-Rousseau was that if you take a hypersurface like that, then either of the Green-Griffith locus is not the whole hypersurface or it is empty, depending on whether you have taken D large enough or a little slightly larger than before. So depending on this, in which case you want to. Okay. So now let me explain what was the strategy to prove these results. A strategy which was used, say, since the beginning. It was used at least before 2010. It was actually an idea of Hsu in the beginning. So the idea is to use the family, the universal family of hypersurface. This is very natural since we want to prove a result for generic hypersurfaces. So what you do is that you fix D and N, your data, and look at the universal family of smooth hypersurfaces in Pn+1. And now you can do what all the constructions I presented before, you can do them relatively to the base in this universal family. And you get space of relative kth kth order differential jets. Sorry, a relative space of kth jets on XD. So here the jets are taken in the vertical directions related to this projection. And also you can projectivize these vertical directions and get Green-Griffith, a relative Green-Griffith jet space for any order K to your universal family of smooth hypersurfaces. Similarly, you can construct the Green-Griffith base loci for any K inside this inside the fibers of this family. And what you want to prove, the goal is to prove that if you have taken D sufficiently big, sufficiently large, then either the Green-Griffith locus, sorry, this should be D here, is empty, or not the whole hypersurface. And it will have given you the two results that were stated in the theorem here. So for generic hypersurfaces, you want to say that this locus with so this locus here with the K is replaced with D actually is empty, or at least not the whole fiber gen. And so, as I said, a way of doing that was presented in around 2010 by Hsu. So it was the strategy of slanted vector fields. So this is a strategy in 2 steps. So to explain it, I will need to introduce the tautological line bundle, this time with respect to the projection towards the projective space in which the hypersurfaces lie. So let me call that OP1 plus 1. So the strategy is in 2 steps. First, you need to find vector fields on the universal family of hypersurfaces, and more precisely, vector fields on their nth jet space. So here, what it means is that you need to look at the tangent vector fields, the tangent sheaf to the universal family, well, to the Gn of the universal family of hypersurfaces, tensored with something which should account for the poles you allow for your vector fields. So you want to prove that this tensor product is globally generated at least above the generic point of your universal family on the base of your universal family of hypersurfaces. So you look at the vertical tangent vectors to your space, possibly with the pole of order beta inside the hypersurfaces you are considering. Okay, so you want to prove that it is globally generated, but it is okay if it is not globally generated above the singular locus of this. Sorry, I realize I might be mixing n and k a lot of times in the future, but in this strategy, n is equal to k actually, so it will not matter too much. So you fix the order equal to the dimension of your hypersurface. So such results with explicit values for beta were proved by many people. So let me quote Bone, Merker, Daronvo, for example. Also, it was used in this Di-Vaio-Merker also works. So let me call, for future reference, Z1, Z2, etc., global generators of these vector fields. Okay, second part of the strategy, prove that you have at least one jet differential on the generic hypersurface. So you want to find some alpha and m such that you have a section of the Green-Griffith tautological bundle on xk-gg that vanishes on your hypersurface, at least at order minus m alpha, or at least at order m alpha. And so m here is not, it should be large enough, but its value will not matter actually. So you want to prove that this bundle is effective above the generic hypersurface inside this universal file. So this with effective values for alpha was proved, well, was obtained by different people. So for example, Di-Vaio, Merker, Demailly. And let me say that such a result in the second case will hold if D actually is large enough. So that's where the hypothesis that D is large enough comes from. So let me call sigma a section of this line bundle defined on the universal family, or at least above a Zariski open subset on the base. And so,
so just to make sure
yes,
that
yes.
In the strategy, so you just use the nth order jet. So where
Exactly,
n
yes.
is okay. So you don't
Yes.
care about other.
Yes, actually the computations become harder if you want to climb up the tower of jets. You cannot go below, so this is proved by Di-Vaio actually. If you go below n for the order, you don't have any such jet differentials. So n is the first step where you can hope to obtain such a jet differential. And if you climb up the tower, if you replace n here by higher orders, actually the situation becomes more complicated. And in this strategy, it's a weird fact, but if the degree, you have to take higher degrees to obtain the existence of such sections. So n is in some sense optimal.
Okay.
So at least for hypersurface. So we have general results, which tells you that if you have a variety of general type, then you have to, and if you let the order tend to infinity, then you will find jet differentials. There will exist certain jet differentials. So it's an existence theorem that was proved by Demailly, but it is not effective. If you want effectivity in this alpha here, N is in some sense optimal.
Thank you.
Thank you. Okay, so now the second step of the strategy is to use these vector fields here to differentiate your section sigma and to get other jet differentials. So this was the idea of Sirocci. So you differentiate the section sigma, you pick a number R of these vector fields, as many as you want a priori, and you differentiate your section sigma. But if you remember, the Zi had a pole of order beta, and the sigma was vanishing at order alpha, say, along a hyperplane section inside the generic hypersurface of your family. So what it will give you is, so it will give you sections of these power. It turns out by some twist, so it accounts for vanishing, or maybe a pole along a hyperplane section on your generic hypersurface. And so if you manage, sorry, R lower than M was not quite, okay. Yes, okay, this is still true. If you have these two assumptions, then you have negativity here. So you get a section of your Green-Griffith tautological line bundle vanishing along an ample line bundle, and then all the entire curves should satisfy the equations provided by these sections. So as long as you don't take R too large, and as long as you were able to prove the two steps before with alpha larger than beta, so you have to prove effective results with alpha larger than beta, then you get negativity here, and you get many differentials that you may use to prove that this augmented base locus, at least outside the singular jets, does not dominate X if X is the generic hypersurface. So it's an idea of differentiating your holomorphic differential equations in directions inside the universal family to show that generically, if you are able to prove global generations by these vector fields here, you may prove that this, you manage to prove that this does not dominate the generic X, and so you obtain the following criterion. So you can put the strategy together and end up with the following criterion. So using the results actually for the effectivity of, using the value of beta that was computed by Darondeau, and Merker before him, but Darondeau gave the better result, you manage to prove the following. So this is the first step of the strategy with beta equal to n 5n plus 3. So if you prove that, okay, so using the first step of the strategy, you manage that if you prove this thing, which is the second step of the strategy, sorry, with alpha equal to 5n plus 3, then for the generic X, the Green-Griffith jet locus does not equal the whole X. So this is the second step of the strategy once you have proved the first step, which is due to Darondeau, Merker, and other people. And so what was improved in this Bergzik 1 results actually is the bound on D for this thing to happen. And so the first step of the strategy was not improved in any way. This is only the second step. Okay, and so let me also say that here you have obtained that X is not equal to its Green-Griffith locus, so it proves that X is quasi-Brody hyperbolic. And if you want to obtain genuine Brody hyperbolicity, you can use, so I will not give, not talk too much about it, but you have this very striking result of Riedel and Yang, which tells you that once you have proved this for D larger than some degree Dn, then you can take a degree even larger and precisely given by this bound, actually, 2n plus 1, d to n plus 1, with dn is the degree for this to hold, then it gives you actually that ggn is actually empty. So it's an argument which, again, is variational. So the idea is to prove the result for hypersurfaces inside P to the power hypersurface of dimension 2n plus 1, and then cut them out by n plus 1 hyperplanes, and show that generically, by letting these hyperplanes vary, you are able to prove that you may increase the codimension of this Green-Griffith space to obtain it at the end that it is empty once you have decreased to the dimension n, starting from the dimension 2n plus 1. Okay, and so with these two results, you obtain the theorems I presented at the beginning of this talk, the proof of the hyperplasticity of generic hypersurfaces. So everything boils down to proving that this divisor, this line bundle, say, is effective on the Green-Griffith space of order n. You may want to prove it is effective. It turns out that it is easier to prove that it is big. So I will explain that in a minute. But before that, just let me, okay, so this is what I said. We want to prove that this is big. Okay. And a strategy to prove the bigness of a line bundle is well known, actually. So you can use the Sue's algebraic Morse inequalities. So it's a criterion for bigness, a famous one, which tells you that if you write the line bundle as a difference of two Neff line bundles, A and B, and if you have positivity of this intersection number computed with this A and B, then L is actually big. So this is very famous. You might find it in Lazarsfeld's book, for example. And so to sum up, you want to apply this criterion to this line bundle on the nth order Green-Griffith jet space. So let me write it down precisely. You write this as A minus B with A and B F. And you want to show that if you have taken your degree large enough, then this number, where n is the dimension of the nth order jet space, then this is positive. And here,
in the inequality,
yes.
so displayed inequality, do you mean L to the n equal, you want L to the n to be an minus n? Yeah, you have something L equals.
Sorry.
What do you mean? Yeah.
This L here should not be here. Sorry. This is a typo.
Okay. So
you
just
you remove. Sorry. You remove this.
Okay.
This
okay.
is yes. Sorry for that. No, of course, this does not make any sense. This is an integer. This is an integer. And this is a line bundle. So this equality here should not be here. I mean that you compute this integer. This is here, the version for the nth jet space over on the hypersurface. You compute this integer, and if it is positive, then you have proved the bigness of your line bundle. And so this integer, if you write everything down, will turn out to be a polynomial in the degree d of your hypersurface and your dimension n. And so what was basically done by everyone in this field was to find a way of, find this A and B first, and then find a way of computing this polynomial, which is not an easy task, and then prove that it is positive if you take your D high enough. Okay, so more precisely, so everything I presented here was using Green-Griffith jet spaces, but in the past, people used actually different jet spaces, more elaborate ones. So, for example, Di Vaio, Mercalrusso didn't use Green-Griffith jet spaces. They used rather a version which was constructed by De Mailly, which is related to what we call invariant jet differentials. And so they have the same basic properties. So you have this tautological line bundle on them. You have the vanishing theorem. So you can construct Green-Griffith locus with respect to these spaces, but it's a bit different. It's a different version. And so what they obtained using this space was some exponential bound. And the reason why they used this space might be because computing the polynomials, the polynomial I presented before, seemed to be seem at least to be possible in principle on these spaces. A feature of these spaces, for example, that they are smooth. So the intersection theory of them is is quite well behaved, even though it is quite difficult. And so what Bergze and Kirwan did actually was to replace the use of this Thomae jet space by a different version constructed using non-reductive GIT techniques. So it's a non-reductive GIT, say, quotient of your JKX, which you can also interpret of the projectivized functor applied to some algebra, which is quite hard to describe, actually. So you have ways of describing it, but it is not explicit in that paper, for example. And then on this space, you also have an intersection theory, which you can use to compute the polynomial of before. So it's not that easy, but you can write, you can write residue formula to express the numbers that I presented before. And you can show that it turns out to be positive if you take d larger than some polynomial. Okay, so these two spaces are, so the first one is quite easy to describe, but the computations are not that easy, actually. And the second one is not that easy to describe, and these non-reductive GIT techniques are, might be a little bit difficult. And so what I realized is that you can use what I presented to you without any, the inputs you need are very few compared to what I presented to you. And you also get a polynomial bound, actually. So it's not n to the power 4, it's n to the power 5, but it is still polynomial. It's much better than the exponential bounds that were obtained using these Thomae jet spaces. So what I want to present you now in the last 20 minutes is actually how you can write this bundle I presented before as a different sort of 2 Neph-line bundles, and how, at least in principle, you can compute this polynomial I presented in the end. So in the end, of course, everything boils down to a computation, which is maybe not that nice to read, I don't know. But at least computing the number is very easy to do in principle using weighted Segre classes. So this is what I will explain to you.
So does this also indicate that working with XGG is equally good as X?
Yes, exactly. So it seems to me that this space is already very, very nice to do. So the intersection theory on this space is very, very nice, actually.
It's a smooth orbifold.
It's a smooth orbifold, yes. So you can, and so the numbers you want to consider, you can, so you have this intersection theory which make appear the tautological line bundle, and the powers of this tautological line bundle, you can actually compute them using Segre classes. So this is what I will explain. So to do that, what you can use is so it's a construction which was quite implicit actually in, for example, in a lot of works of Thomae, which is related to the fact that there exists a deformation of the kth order jet space to sum of copies of the tangent bundle to k copies of the tangent bundle above X. So the first one is not a vector bundle, but it deforms to a vector bundle. So a deformation that simply means a space that lies above X times C, such that if you look at 0, then or at outside 0, you get the two different versions. So above 0, you have this tangent space, k times, and outside 0, you have this JKX. So somehow it's a test configuration. If you are familiar with the idea. So here it's an affine version, but in the end, once you projectivize it, you will really get a genuine test configuration for the Green-Griffith jet spaces if you are familiar with this notion. And so the idea is simply that if you want to look at the change of coordinates for jk above x, you have this Fadi-Bruno formula, which tells you that the kth derivative of z composed with the change of coordinates looks like that. So you have first a derivative of phi. So it should be a Jacobian matrix, of course, but let me write this quite quickly. And a nonlinear part, which depends on all the derivatives up to order k-1 of z, and the partial derivatives of this diffeomorphism phi. And so if you take a lambda in C, varying in the base here, you can scale this down and in the end get something with changes of coordinates, which are exactly given by k Jacobian matrices, giving you this structure of k copies of the tangent above x. So there is okay. So once you projectivize it, you may say that there is a deformation of the quotient of this jkx minus the zero section by C star to the exact same thing, but with the copies of the tangent bundle k times. But here, just be careful, the action of C star on these copies are given with different weights. So you have weight 1, weight 2, weight k. And it gives you, of course, well, it gives you a deformation of xkgg to another bundle, which is also a bundle in weighted projective space. So again, you can look at it as a Green-Griffith, a Delignum for stack, the smooth or default above x. And so I will use this notation to write this space. I will call that a weighted projective bundle, and I will use the exponents here to emphasize the fact that you have this action with weight 1 on the first copy, with weight 2 on the second copy, etc. once you quotient by this star. Okay, so you have this. And let me also say that you can write this weighted projective space as the proj of some algebra, which is given by the symmetric algebra of a sum of copies of the cotangent bundle, but again, not generated in degree 1, but generated in, this should be 1, 2, 3, etc. until k. So you put a copy in degree 1, another copy in degree 2, etc. until k. You take the symmetric algebra of that sum of copies, and if you projectivize this symmetric algebra, then you get this space. And as a proj functor, you also have this tautological line bundle, OPK1. And one thing I can say is that if you recall, the Green-Griffith jet spaces were also projectivized algebras. Well, the proj functor applied to the algebra of Green-Griffith jet differentials. Another way of looking at this deformation is saying that it is what we call the Riesz deformation applied to some filtration on the Green-Griffith algebra. A natural filtration that was known for some time, whose graded object, whose graded algebra is precisely that one. So you have a way of passing to the graded object of this filtration using a deformation of the algebra. Okay, so the geometric picture is as follows. So let me write it down. So above x times c, you have a deformation of the Green-Griffith jet spaces, as well taken with their tautological line bundles, such that you have, okay, maybe say that first. Outside 0, all the fibers are given by the Green-Griffith jet spaces with their tautological line bundles, and on the fibers above 0 is precisely given by that space with its tautological line bundle. And the deformation is also locally trivial above x. So locally above x, you don't have any change of coordinates to do, so you can directly trivialize on jkx, and this construction doesn't do anything then. Okay, and you can use this construction to write, so if you remember, we wanted to write some line bundle as a difference of A and B with A and B in F. And this construction is very convenient to find this A and B. So assume that X is a degree D hypersurface. A fact which is very easy to prove is that on this projectivized bundle, PK, then the tautological line bundle tensor by twice the hyperplane bundle on your hypersurface is Neff. And good proof of that fact. So I don't give the details, but the basic idea is that simply the cotangent bundle plus twice this hyperplane section is globally generated. And so you can use the fact that this line bundle is actually the tautological line bundle of some shift of the algebra you use to so I will display the algebra. Some shift of this algebra has as a tautological line bundle this one plus twice the hyperplane section. And so you show that all the bundles that appear on these twists are Neff, and it gives you the required Neffness, and everything boils down to using that fact actually. So it's a very easy. And as a consequence, since you have a Neff line bundle on the central fiber, you have these semi-continuity properties for Neffness with respect to the very general topology, which tells you that outside of the central fibers, you have at least one point where this is also Neff, and you also get the Neffness, but this time on XKGG. And so now you may write your twisted tautological line bundles, the difference of two Neff line bundles, A and B, with so I hope I didn't mess it up. So A is that one, so the one we had before, and B is just 5n plus 5 times the hyperplane section on the hypersurface. Okay, so you have your A and B, and now you want to compute your intersection number. So let's do that. Recall that you have written A and B that way. And the goal is to compute this number, which is an integer. Okay, so how to do that? So you can use the fact that the deformation before, so it's a topologically trivial deformation, actually. You can use it to compute the intersection numbers on the central fiber. So in the computation, you may replace this tautological bundle for the Green-Griffith jet differential with the one of the central fiber, which is the tautological bundle on the weighted projective space. And this is much easier to do. So let me show how to compute n8 to the power nn, at least in principle. So I introduced the following notation. So C1 of A, the first Chern class of A, I imply the pullbacks. So it is, sorry, the tautological line bundle of PK plus twice the tautological line bundle of the hypersurface of the twice the hyperplane section. Okay, so I will not, of course, present you the full computation, but just let me say that if you put it to the power NA, this is what appears. It is a sum of some binomials in H and U. And such binomials you can actually interpret as Segre classes, because U actually is the first Chern class of the tautological line bundle on some projectivized bundle, a projectivized bundle of some weighted direct sum. So let me formally call this weighted direct sum T boldface K. And so what I claim is that the previous computation, in it, you can replace this U to the power nn minus L times HL by some Segre class in this direct sum. So you get a way of at least describing this number. Now you have to compute it, but this will be quite easy to do using, for example, a Whitney formula. So here, this S boldface is what I call the Segre class of the direct sum Tx with weight 1, Tx with weight 2, etc., until Tx with weight k. So let me give a quick definition. 10 minutes. So let me give you a quick definition of what I just said. So what I call the weighted Segre class for some vector bundles E1 to ER, you can interpret it, for example, as an endomorphism of the Chow ring with rational coefficients. So you can construct it that way. First, form the weighted projective bundle above X by quotienting E1 plus etc. until ER by the action of C star with weight A1 on the first one, A2 on the second one, and AR on the last one, as I said here, with this action. So you have a natural, again, orbifold tautological line bundle on that space. And as usual, you can form a Segre class, you can apply to any Chow element of the Chow ring with rational coefficient alpha, the Segre endomorphism that you may define as follows. So you just want to take actually the intersection of the pullback alpha with some power, the adequate power of the C1 of the tautological line bundle. Here, since it's an orbifold line bundle and not a genuine one, either you look at this intersection number in the sense of intersection theory on smooth Deligne-Mumford stacks, or you just take some sufficiently high power and you just divide by this power in the end so that this is a genuine line bundle, and you define this Segre class that way. Oh, so I wrote for M divisible. Okay, and so in the end, as I said, you may rewrite your A to the maximal power of some using some Segre classes as before, and you can do that for the intersection numbers that appears inside the Sue's holomorphic Morse inequalities. And what you want to prove is that this is positive if the degree of the hypersurface is large enough. So first, compute this in terms of the degree of the hypersurface. And so to do that, so this is what I said here, you need to describe this in terms of the dimension and the degree of the hypersurface. And you just need to apply a Whitney formula. So here I wrote the Whitney formula with the two terms. Here you have K terms inside this boldface Tn. But the general formula looks very much like that. So you have the GCD that appears here. So to prove this formula, it's not too hard if you follow Fulton's book. So I think it was well known before I wrote this, actually. But maybe hidden in some papers of intersection theory on weighted projectives, on the weighted projective spaces. But if you want to reprove it, actually, either you follow Fulton's book. It's also quite easy to prove the numerical version just by computing asymptotics of Euler characteristics and then decomposing everything using the splitting principle. You just have to use the fact that Sn here is the leading term in the Euler characteristic of the powers of the tautological line bundle, and then it looks like what is done in Dobar's book, for example, to define the intersection bundles. So this formula is very not too hard to prove, and if you do what I said on using these Euler characteristics, it gives you computations which very much look like what Green-Griffith did in their seminal papers on Green-Griffith jet differentials. So again, the circle seems quite complete to me. So you apply this formula to this Tn here, and now you have a hypersurface. So this should be Tx. You have a hypersurface, and on a hypersurface, well, you know what is the Segre class of Tx. This is simply given by this. A hypersurface is a complete intersection in Pn+1. So you can describe the Segre class of its tangent bundle just by using the standard exact sequence relating the tangent bundle of Pn+1 with the normal bundle of the hypersurface, which appears here. And this is related, as I said, to the Segre class of the tangent bundle of Pn+1. Okay, and now you have to be quite courageous and put everything in the formula. And it is not that very fun, but it is doable. It's very doable. You just have to express every Segre class in your formula in terms of n and d. So, and you get this polynomial. So it's a polynomial in D with coefficients, rational functions. Well, maybe yes, rational functions rather than polynomials here in N. And so I want to emphasize the fact that in these works of Di Vario, Mercalrusso, Berczikirwan, Darondo, and all these people, in the end, the final product is the same. You write this as a polynomial like that, and you want to determine when it is positive. And so the idea here is to use a well-known criterion. Well, it's an undergrad exercise. Take a polynomial like that and with coefficients am, and assume that am is positive, and then that the other coefficients are bounded as follows with respect to the first one. So their growth is less than geometric with a ratio d. And what happens is that if you plug inside this polynomial a t which is larger than this 2d, then the polynomial is positive. So here, if you look at this polynomial, the variable will be d, the constants ai will be the qln, they will depend on n. And in this polynomial that you obtained using these Segre classes, you can compute explicitly what is the leading term. This is this qln here. I claim that it is positive. Well, this part is very easy to prove. And also, now you can also prove that the coefficients are bounded by the first one with this less than geometric growth with ratio given by a constant times n to the power 5. And so if you do that, you prove that for d larger than some constant to the times n to the power 5, this is positive. And then the previous strategy works completely, and you get hyperbolicity for hypersurfaces with degree larger than some polynomial with degree 5 in the dimension of the hypersurface. So I think I will stop here. This is all I wanted to say. So thank you very much.
Thank you very much. Are there any questions? So do you think that so from Sue's strategy, step 1, step 2, so if we have alpha and beta, and then starting from alpha, beta, and then leading to the upper bound of this part is already quite more or less optimal, or you think there's still some space to improve?
So I must admit that I'm less familiar with the first step of the strategy, so the construction of the tangent vector fields. But from what I understand from the people working on it, we are quite close to optimality, I think. And in the second step, using this, so using Sue's algebraic Morse inequalities is not optimal at all. So as I said before, you can prove that on a variety of general type, you always have bigness of these tautological line bundles when you let k go to infinity. And here, as I said, we fix k equal to n. And if you use the Sue's holomorphic Morse inequalities I presented before, the situation becomes less favorable as you let k go to infinity, which is counterintuitive, really. But if you want to prove that the situation improves when k goes to infinity, which should happen, actually, you have to use de Mailly's holomorphic Morse inequalities rather than the ones I presented here. And so, or you could also maybe try to use the algebraic version of his Morse inequalities that I use in an earlier work to reprove this existence theorem of jet differentials for varieties of geometry. So I don't know, I am not quite sure what they should give for hypersurfaces. I have not tried to specify them to this setting. So Demailly has some computations, but I think I think they are not optimal, actually. I think he removed some terms in these computations that maybe should be worth looking into because the short answer is that I don't know, but I think that there are different techniques beyond Sue's algebraic Morse inequalities that may permit to give better results. So I don't know if we will be able to decrease really the bound to linear ones. And if I had to bet, I think Sue's strategy is not enough actually to obtain these linear bounds. I think other ideas are needed, which should be the ideas that need to be developed to attack the Green-Griffith conjecture in full generality, not just for hypersurface. I think there are problems that we are not yet able to understand with respect to using only this strategy of jet differentials. But maybe there is still room for improvement still using these different versions of algebraic Morse inequalities.
Mm-hmm. And why can we get n to the 4 using non-reductive GIT?
I must confess that I don't really understand. I don't really know. So in the end, it is just what happens in the computations. So in Bergzik-Irwan's work, the computations are presented in a very different way from what I presented here. They are done using this residue formula to express the intersection number. And in the end, the computation is just different. It's not the same, and I don't have a very conceptual reason for why it should be different. So what I would like to do is to reinterpret their work using these several classes I presented here. And I think this is, I have some ideas as how to do it actually. But maybe in that way we will better understand what is the difference, the gap between the two spaces, which should be quite interesting, I think, conceptually. But first, you have to write. So understanding the space from a non-reductive, they constructed their spaces using non-reductive GIT techniques, but actually there are also different ways of constructing them that are, I would say, more geometric in flavor. And on this, using this construction, I think you have a way of putting Struggle classes in the picture to express differently their numbers. So maybe in the future we will understand better what happens.
Mm-hmm. And what about complete intersection in the projected space? Are there some conjectures and or no results?
Yeah, so you should expect to improve the bounds once. So you know that if you get to half the dimension of the hypersurface, then you get ampleness of the cotangent bundle with, again, degree high enough and generate hypersurfaces. So I have not thought too much about that. So, if you, yes, you can try to look at all the intermediate dimensions between 1 and n/2, where n is the dimension of the ambient space. And conjecturally, it's natural to expect that you will. So this is quite related to some work by Antoine Etes, actually, who precisely did that. So also Demailly has some work studies external powers of the cotangent bundle. But I don't know if what I presented to you using these Green-Griffith jet differentials will what it should give related to the degrees of the hypersurface. So maybe it's worth looking into it. No. we arrive at the end of the times. Be the rule.
Sorry. I think the connection.
Yeah, no problem.
Yeah, we lost the connection. So I'm sorry. So let me set you again as co-host.
Okay.
You are still co-host. So
yes. Well, I stopped
could you,
sharing my screen.
Could you try to?
But I don't think I have anything more to show. Well, you want to see my slides again?
Because we completely miss your answer to the question about complete intersection. So
okay.
Yeah, the connection was lost.
Okay. So what I was saying is that you have this solution to the Debar conjectures, which was obtained by Rondeau and Brodbeck, which tells you that if you have you take Pn, or it also works for other varieties, but say you take Pn and a complete intersection of codimension higher than n/2. And then for such a generic complete intersection, you have ampleness of the cotangent bundle. So it's much better than saying that you have many differential equations, because you have showed that you have these differential equations at order 1 and not merely k equal to n. And what I was saying is that different people have worked on trying to obtain intermediate results between codimension 1 and codimension n/2. So, for example, Antoine Etes has some work on these things. Demailly also has worked on this problem. And I don't know if the computations I presented, which are related to Green-Griffith jet spaces, what they will tell you if you take intermediate situations between, say, 1 and this n/2. So, for example, what you can yes, so I think it should be quite interesting to look at this problem, but I must admit I have not tried to do it, maybe for the time being.
Okay, thank you. Are there more questions?
Thank you.
Yeah, there's one question.
So given X, which should be like a degree D hypersurface of a projective space, do we actually have an explicit description of what the Green-Griffith locus is?
No, I think it's very hard in general.
Or do we know whether it's like irreducible or any
dimension?
Geometric, dimension,
No, I don't think we have such information. So what I presented to you is quite coarse, actually. We said that it is not the whole space, or it is empty. So the idea, the theorem by Riedel and Yang that I didn't really present, actually, is something that speaks about the codimension of that space, and they show that you are able to bound from above the codimension of this space if you take, so say you take a hypersurface in dimension n, a generic one, and you show that the Green-Griffith locus is not the whole manifold. Then what they prove is that a generic hypersurface of the same degree, but this time in Pn-1, has a Green-Griffith locus which has codimension increased by 2. And then in the end, they show that it is empty. So it's an upper bound on the codimension of the Green-Griffith locus somehow, but it doesn't tell you anything about its genuine codimension, and neither of its irreducible components. So I don't know if in more specific examples, we have more information on the Green-Griffith of this. So one thing I did not say is that we cannot expect this Green-Griffith locus to be empty for a variety of general type. So, or at least not the whole manifold. So, if you look at the general conjecture, which tell you that for X of general type, there should not be any dense entire curve, you might think, okay, it is enough to prove that the Green-Griffith locus is not everything. And you might wonder if this is true if for any variety of general type. But this is false. There are examples of varieties of general type where the Green-Griffith locus is everything. And a very simple example is a product. So if you take a product, then the Green-Griffith locus is everything. So I don't know if for hypersurfaces, similar phenomena can happen. I don't think this is the case, but I am not aware of any examples where the Green-Griffith locus is computed explicitly.
Okay,
So,
so
yeah, I
does
think it
the
would be interesting to
Green-Griffith
have that.
locus appear anywhere else apart from the proof of this theorem?
Oh.
Like, why was it discovered in the first place?
So I think that what's discussed first was the vanishing theorem I presented in the second part with the simple fact that entire curves satisfy the holomorphic jet differential equations that you can define on your manifold. And it was not stated by Ring and Griffith in terms of a locus. They did not introduce this locus but it was more or less folklore, I think, in the minds of people working on that problem. And so I don't know who first introduced that locus. The first occurrence I am aware of is, I think Stu did it. I'm not sure. But for example, what I said about the fact that for a product, you have equality between the Green-Griffith locus and the whole manifold. This was explicitly remarked by Merker and Di Verio, by Di Verio also. And they introduced explicitly this locus, well, as a way of stating quite differently the vanishing theorem of before. But outside hyperbolicity, I'm not sure this appears, for example, or it is it's an intrinsic locus that you can define on any manifold, on any projective manifold, but I am not sure whether it appears in any other fields that complex hyperbolicity. So maybe some people are working on it, and I am not aware of it actually.
Okay, thank you.
Thank you.
So in the statement of Green-Griffith conjecture, if we replace the existence of entire curve by the existence of non-constant map from P1 elliptic curve and abelian varieties, so does it change the statement?
Yes, you can state equivalent, well, you can state different variants of this conjecture. For example, looking at rational maps starting from abelian varieties. And so we expect all these conditions to be equivalent. So you can introduce different loci, map starting. So for example, in a surface, the conjecture should boil down, should be equivalent to the fact that there are no P1 and elliptic curves in your surfaces, in your surface. So this is just saying that you have no curves which are not of general type. But as you said, so recently there is, yesterday I think, there is this paper of Campana and one of his co-authors whose name, in which they precisely discuss this question. So you can look at it and you will have, you will see that if you assume the general conjectures of the field, you have different loci that you can define on a variety using, for example, abelian varieties. Which should turn out to be the same, or at least included in one. But strictly.
Thank you.
Thank you.
So are there more questions? So if there's no more question, then let's thanks Benoit again for the very nice talk. So thank you very much.
Thank you very much.